Okay, everybody, this is lecture number 5, and it is on Unix tools. And the title of this is about 45 slides long. The title is a little deceiving. Admin tools. What does an admin do these days? Well, it's actually a little deceiving as a title because it's just talking about Unix, miscellaneous Unix stuff. And this is all things that admins do. And it starts out in the review of this kind of looking at file manipulation and utilities, Unix processing subsystem, and an overview of the Unix shell environment. So this talked about Perl. And I like to cover Perl first because Perl, really gets people excited sometimes about scripting and really, provides a better language. It's more feature-rich. And when you start seeing the shell stuff, then you know why people use Perl. Because the C shell is really limited, and scripts themselves are kind of limited. You can write them in C. You can actually do programming in them, but functionality isn't really as feature-rich as Perl is, and it's not very extendable. So in terms of the file manipulation utility, most admins, what do admins do? They create files, and these files are scripts, and these files are setting up directory locations and file access to users. They're administrating and managing disk space. They're using a lot in terms of it's very file system oriented, what admins are doing actually these days. They're running things to back stuff up, transfer stuff over, configure something, give somebody access to something, takes access away. So knowing something about the file attributes and files themselves kind of makes a little sense. And as I mentioned in the first weekend, I talked about the file system in the introductory lecture the last time we were here. Everything is stored in a file. Everything is stored in what's called inodes, and the inode system is what initializes, and it kind of runs in memory. So we don't do any direct reading and writing to the file system. And if you remember what I said about the inodes is a huge old, call it a table for lack of better words. It really isn't a table. Instead, it's like a memory system that combines file systems from multiple different devices, multiple different places on the network, puts them together abstractly as one whole unit, and all of the information about all the files is stored in the inodes. So if you've got a corrupted inode system, you're on FSCK, and that works on the inode and the file. It's a file system check is what it is. And when you're checking the file system, what you're really doing is traversing through the inodes and fixing mistakes so it matches what's on the disk. Because it's kind of like lost files and file allocation errors that you get in a Windows, in a FAT system that provides an interface to the file system for FAT. Inodes are the equivalent for Unix. You can check them, fix them, do all sorts of things with the inodes, but the inodes are primarily what the admins are using. Permissions as well for reading, writing, and executing. We went over the commands for this in the first weekend session, but to explore the concept from a system administrator perspective. File modification times, file types are also stored in terms of attributes, regular file, link, symbolic link, special files. Because as I mentioned before, everything is a file in terms of the abstraction. So we have some files that are directories, some that are devices, some that are really files in terms of what's being stored on the hard drive. So we have some utilities for manipulating file attributes, the change mod, the change the file mode or the position permissions, which makes it read-writable, executable. And we saw this actually in the Perl lecture, but didn't really go over the command. You would type in change mod space, some numeric code. I'm going to go through that in a few minutes to change the attributes that are associated with a file to make it executable, or to make it hidden, or to make some change to it. You can also change the file owner because Unix admins, they're mostly concerned with keeping everybody's account separated. One file owner or one group. So they're creating the groups, they're creating the privileges for the groups in terms of the access. They're monitoring the usage of different groups, uses of different owners, which owners own which files, and there's an entire protective system if you think about it. There's different levels of access with different levels of permissions. As an example, root or admin on most systems has access to everything. When you log in on your user account, you're not an admin, you only have access to your stuff. You have mappings or access to programs and utilities as a user. So That's something that system administrator is taking care of. We can also change the file group. So we can change file owner, file group, permissions themselves. Only the owner or the super user can change file attributes. And most people figure out real quickly, especially if you do a default install of any Linux system, you find yourself having to type in SU a lot to give yourself supervisor privileges, unless you're logging in as the admin or you're logging in as root. Most modern day systems, they call it root. In the old days, you used to call yourself admin, which is where system administration got its name from. Sounds much better than system root. You're the system rooter. No, you're a system administrator. Okay. So instead of calling yourself an admin, now you call yourself root. Anyway, but your account usually called root these days. There's actually, Oracle refers to it as system. You log in as system, which is supposed to be administrator. So different names for it. They all mean the same thing. It means you have access to everything. Upon creation, default permissions are given to the file modified by the process called umask. And umask is a value that's associated that keeps track of the permissions. So there's three types of permissions: read, write, and execute. And I can kind of go through this pretty fast because as users, you already are familiar with this stuff, hopefully, if you've ever used a Unix system. There's three sets of permissions. They're for the permissions for the owner, the group, and the other. And you can access checks made against processes' effective IDs, which is essentially going to, give us the information that comes back. So we have symbolic access modes. And so these are the octal access modes that are associated. And I actually went over this already in the first weekend session when we talked about Linux commands and when we did the overview of Linux. So I'm going to kind of skip through it because we've already covered this. But knowing that you can use the octal number or you can use read, write, execute in terms of the permissions. The format for the command in this particular case, change mod plus R gives read, add read privilege to the particular file, or you could say change mod space 777 and then the name of a file or a name of a directory, and then you've pretty much opened the door, made it public for all three groups essentially. And the numbers actually come in sets of 3 because you've got a set number between 0 and 7 for the owner, the group, and the other, which are the 3 levels. So normally you'll see if it's an HTTP public HTML subdirectory and it's made for web access, you'll see 777. If it's a private file, you'll see 640 or something like that, which is common numbers. So Unix administrators, not to say that they have nothing better to do, but they end up having, through time, memorize this really weird stuff. All the number combinations like 640, or 777 and stuff like that. And it's only because after you do it 100 times, you just kind of know. And then you can do an ls on it and you can actually check what's set. And then if you don't set something correctly, it ends up causing a protection problem in the future when somebody else is modifying somebody else's file. You never want to set something, or actually, users have the opposite problem. When you're first learning web development and you create a public HTML directory and you put your files in there and it says, access denied, insufficient privileges, and then I have to set it to 777, or actually you don't. It can go 750 or 755 is probably pretty normal. Because why do you want the outside world to be able to edit your files? That's pretty dangerous. So you just want them to essentially be able to read them, access them. And there's an entire thing in terms of directories as well. If the directory is not public, well, are the files inside of it public? Probably not. If you can't get to the directory, it's all hierarchical. If you can get full access to the directory, can you get full access to the files? No, depends on the files at that point. So admins are primarily interested in mapping all this stuff, and sometimes you see charts or you see graphs of the directory tree, and it's all written out. You see all the branches and stuff that go off of it. You can kind of see that there's like a pattern to this, and there's a common pattern that most people follow. Like bin is holding all system utilities, shares, all shared files, users is the root directory for all the user accounts and stuff. So read means the process may read a directory or a list of files. So you can read a list of files even though you can't access them if you put read on the directory permissions. Write to a process, so your process can add or remove files in the directory. Execute means that you can search the access files, the directory, the subdirectories. There's some common utilities for maintaining files and directories. To print the process current directory, pwd. To create files, the cat, the ed, the vi, I'm not going to go through all these, it's kind of boring. In fact, we covered this in the first interactive session, so you can review all of the different file commands themselves. Let's talk about processes. So let's move right along. So every single program, and I mentioned processes when I talked about CGI. When you go through the CGI port and you run a Perl script, even though it's a script, it still runs in the form of a process. So if you run a C program, it still runs in the form of a process. And so Unix is actually one of those original concepts of multi-processes or multi-programming environments. So in the old days, actually in the old DOS days, if you think about it, DOS still runs like this, actually. The processor worked on one command, and the processor still they only run one command at a time. So the process would pick up a program, load it up in memory, and run it, and then would pick up the next program. If you're at a DOS console command and you type something in, you wait for the results to come back, and then you type another command in, and wait for the results to come back. That's a single process. That's a single mode, single-threaded type of environment. They call it threads to define the threads of execution. Each program turns into a thread mapped to the kernel. So out of the user mode, on modern day Unix systems, even Windows systems run the same way, we have multi-threaded multiprocessors. And what that does is it handles, the kernel keeps track of multiple programs all running simultaneously. Obviously, how can you have Windows without, and Windows actually on the DOS environment was the first multi-threaded kind of implementation of that same concept on a Windows PC instead of on a Unix environment. Unix has been around forever. But they say, hey, let's just put this on Windows. And put it on Windows, well, how many people would buy Windows if it only ran one program at a time? People used to do that in the past, though. But now you load up your Windows, and if you don't have 5 screens open, you don't have your email running along with your web browser, you're not going to be a happy user. You're not going to buy that operating system. In order to make that possible, each one of those programs that's running is running in its own process space, and it's created in the abstraction of its own process. So when you double-click on a file in any operating system these days, the kernel opens up a new process, allocates memory, and process is nothing more than the allocation of memory and keeping track of which memory belongs to each running program. So the kernel has got a process control block, which is a table, a hash table actually, that has a lookup that says, process number 1, I loaded up my Windows and I double-clicked on Microsoft Word and I opened it up. And so when you do that, the kernel comes down and says, oh, new process, new program, no problem. Open up some memory space, load the program code in there, add your entry into the process control block and say, oh, okay, you're process number 1. And if I went out into the terminal prompt and I typed in PS, which is short for process, I would see process number 1, MS Windows. Okay, good. So the user knows about the process as a kernel. Double click on another file, same thing happens. So I end up with what's called a process list, sometimes also referred to as a job list or program list. And the program list is what the kernel juggles, and every one of them is in the form of a process. So from a Linux and a Unix perspective, this is the core concept of running anything. This is the processing that's going on. So by definition, the program is a collection of bytes and data that is stored in a file. The program is what's physically double-clicked on. It's that exe executable or the Perl script. Then we have the image, which is the computer execution environment, which is the abstraction of the process in memory and the control of that process. And inside of the process, we have the heap, and it's just storing that dynamically allocated memory. And then we have the stack, and we have the runtime engine, and all the different components in there that are controlling the execution of that process. And so the process itself is the execution of the image. A process is not really a process of different process states. And in Windows, we can press Control Alt Delete, go to the task manager, and actually look at all the running processes that are going on. In a Linux environment, we type in PS, we see the same thing, or jobs. So it creates multitasking, long story short. Many processes can execute simultaneously in Unix. It is more multiprocessing in Unix than it is in Windows. because Windows still runs on top of DOS, which is why in the old days when XP came out, and XP was actually a good advancement, you can still, even with 7, you can still go to a DOS prompt. But what they did is they moved it. They moved it so now DOS is a shell. In the old days, you booted up the computer, it went to DOS, you typed in WIN, and it brought up Windows 3.0, and it was a program running in DOS. And the program loaded up programs inside of the program, and it kept it. And that thing ran slow, very slowly. So the more you make it into a Unix, which is why some people claim, oh yeah, MacBook, oh yeah, much faster. OS X, oh yeah, it's running on a BSD Linux kernel. You're not running on a DOS system, you're running on Linux. And so you've got multiprocessing built into the core kernel, and you have control over those processes from a kernel load, from a kernel perspective. You do not have that. Even in modern day Windows 7, you cannot program in threads. You cannot create processes on a Windows system. So you take a Linux system programming course, you actually have to load, you have to buy a MacBook, or you have to load on a Ubuntu disk or something like that and do your thread programming on a Linux system or Unix system, because Unix, the base core implementation, is from a process concept, and it's the underlying foundation for the multiprocessing. On Windows, it's an afterthought. It's an abstraction built into the Windows kernel that runs on top of DOS. No control from a user mode perspective. It's all controlled by the program that's running. So if you really want a true multiprocessing environment, you go the Unix route, or the BSD route. So Unix process groups, and this is the interesting part, so everything on the system, even the kernel, runs in the form of a process. So if the kernel is a process, and it's aware of all of the other processes that are around it, you can build process support into it. It's kind of like, if you're a student and you have access to the other students, going back to that Bluetooth chat example, you have access. All you have to do is turn on, hey, make myself discoverable, and now I see everybody else around me and I can go and communicate with all those people. So Unix provides interprocess communication from a kernel level, because the kernel is also a process. It's not something else. In Windows, it's something else, which is why you don't have kernel level support for processes on Windows, but you do have it in Unix, which is kind of interesting. This takes like a week to explain to systems programmers. First, if you ever taken a Unix programming course or systems programming course, first question that comes out of the students, can I use my Windows system for it? I mean, not unless you install a Linux partition, maybe, but you can't create a thread. And you got libraries now that work with .NET where you can simulate it. Java, you can simulate it. You probably should know that already by what I said earlier today, because Java just loads an operating system on top of an operating system. You're not working with, on Java, you can actually do thread programming in Windows, because you're not working with Windows. You're working inside of the JVM, which is a Linux-like environment that provides thread processing support. So it's a different operating system. You can load it on top of your operating system. Alright, so that's the foundational material. The concepts is that each process has an ID, has a process group that's associated with it, and has a foreground processing group and a background processing group. Why do we need to know that? Well, how many simultaneous users do we have logged into the system? How do we know which user loaded which program? So the kernel keeps track of who loaded up which process. Processes have owners, they have process groups that are associated with them, and they have process priorities that are associated with them. And so we have process relationships that exist between the processes. A process spawns another process using a fork system call. It creates processes. So the creating process is the parent, the child is is owned by the process. So it's a newly created process. And the entire system starts out from init, I-N-I-T, which is the main user level process that starts the entire system of the abstraction that you're familiar with. So first thing that happens when you boot up a Linux box or a Unix box is the kernel has to load. Where's the kernel? Well, some boot disk, some partition said, go load that kernel, probably from a grub menu or something. Kernel starts up. Kernel just starts starting processes, one process after another. Finally, we get to the last process, and then the last process starts the user mode, and that's the init, or initialization. So init sparks off another level of processes. So if you can figure out which processes the kernel started and which processes the user is using, which is pretty easy to figure out, then you can control them in different groups and give them different priorities and different access to the CPU. So you can make the kernel level processes run faster, give them a higher priority, give them more access to the CPU for more critical functionality, and put the user at a lower priority, which is what usually the case is, and make their processes run slower, which gives you a nice even balance. Not only that, but gives you a protective mode as well and all the other features that are associated with the running kernel. It allows for more orchestration in terms of what's going on, instead of having everybody all at one level. Windows, we don't have such a hierarchy. Everybody's all at one level. So if your operating system is doing something, what ends up happening is the user sits there and waits. You can tell the difference when you double click on Windows and you open up Windows and applications and you say, wow, it loaded up fast. And then you close it and you open it up again. Oh, why is it taking so long? There's inconsistency with how fast things open and close. It's due to the priority of the process and what else is running simultaneously with it. And in Windows, we have more interaction, so we have kernel level stuff happening along with user level stuff. There's less of a, you'll wait longer. Long story short, you'll actually wait longer on a Unix system. So if you've ever noticed how a MacBook loads up, slow. By the time the operating system actually gets up there and you load that first program, it loads a lot slower than Windows. Windows, it loads up, takes longer to load, but when it loads up, it's faster. The execution's faster because on a kernel, we've got a BSD unit under there taking control of everything, and users at such a low priority. Until it's ready, until it's going to give you control, it's going to hold off forever. And you're not going to, but the running of the program is probably about the same. It's all processor speed related. The bigger your processor, the faster your execution is going to be in the end. But anyway, long story short, insignificant differences between the implementations from a usability point of view. So it makes it kind of difficult when you think about it, because how are you going to measure? Most people measure the speed of the operating system by how fast it boots. So in the last couple, if you haven't noticed, in the last couple of advertisements for Apple, in terms of, oh yeah, look at it, you turn it on and it loads up fast. Yeah, you just delayed loading stuff, just have it, have the impression of it loading up faster. And actually what you did is you just loaded it on a solid state drive, so no changes were being made or anything. It just stores an image, it reloads the image, so not so bad. You just change the process to give you the illusion. So a lot of the point I'm making is that a lot of the user experience is made up. It's by whoever configured the program and how they designed it to run. And what the operating system is, it's a running program. You're running a program on your computer. And Linux is nothing more than another running program. It's a kernel that's running. So fork returns 0 for a child process, and it returns the process ID of a child to the parent process. So parents can keep track of children. Children don't really know anything about anything else. They run. When they die, execution goes back to parents. So we have a process relationship exists. To run a new program, the child will issue an exec command, run something, terminate it. We have a wait, so the parent waits, because we really only have one thread of execution in each one of our processes that are running. And so one process might actually fork another process. It might fork another process, but at one time only one thread is running. So we can have multiple threads that are mapped to that one process. So they say, what's a thread? Oh, it's a lightweight process. Well, threads are, from the abstraction, can be considered the same as a process, because the programming language implementation, you create a thread, use the thread libraries, and you use fork to create a process. It gives you the illusion that threads and processes are identical. But there's a mapping between threads and processes normally, and you can take all the processes out in user mode and map them to one kernel thread, or you can take and map them to multiple kernel threads, or you could take multiple processes and map them to multiple threads, or you can have a single one thread to one process concept, and there you get the core differences between all of the different Linux versions. Core difference between a lot of the different experimental BSDs versus UC Linux versus BSD is Berkeley, but HPUX, IBM, Microsoft Server has a pseudo Linux kind of thing to it, but all the different versions, a lot of the differences have to do with the process implementation and the kernel implementation. Well, the kernel is the process, the kernel is the system, but the way the processes are managed, kind of interesting how it differs between different systems. But there is a difference, not everybody's the same. So there's a code used for an exit, 0 for success, not successful. So here's an example. There's a program that creates a new process to copy a file. So we have fork. Fork creates child process, runs a program, returns execution back to the parent, something like that. So here's a fork operation after the fork operation. Parent process data, child process data is all sharing the same. So it's a shared text. It's actually inside in a Unix, modern day Unix system, and especially the case for Windows, all threads are inside of the same process. So it's a single process, multi-threaded. So we have multi-threaded programs, which are processes. So in the old days, before we had Windows, we had one process per one thread. And so we created multi-threaded multiprocessing by creating multiple threads inside of one process. And when we do that, we can, why would we want to do that? So we can multitask. We can have 10 different things open at the same time. And how many things are you actually using at the same time? One thing. They're all sharing the same process space, but you can't physically, it's totally impossible. Actually, in this case, I have two. Well, I'm working on a Linux system that does a different mapping. And I'm working with a program right now, actually, as I speak, that's recording. And I have a PowerPoint slide presentation opened up. So I've got PowerPoint running. I've got iShowU, the software that I use, which is not available on a Windows system for obvious reasons. Running simultaneously. And they're both synced and sharing the same, well, they're in multiple processes is what it is. I have multiple threads mapped to multiple processes that are synchronizing the activities. You get more synchronization in Unix than you do in a Windows environment. The program's not available in in Windows. And actually, most of your recording software in Windows is not as good as it is on a Mac system or on a Unix system because of the sheer implementation of those processes and the way the threads are mapped. On a Windows system, it's hard to achieve pure multiprocessing because you've got multiple threads mapped to one process. So, but the design is kind of easy. In a Windows system, if I weren't going to complicate something and I had, let's say this was a Windows partition, and I had PowerPoint open, am I really using Word? No. Do I have an email program opened up? Maybe, but I'm not checking my email right now. I'm only one person. I'm just looking at, and I'm going to switch to PowerPoint, and I'm going to open up my Word. I'm going to open up my Word program, or I'm going to open up my email program. But as a user, you're only working on one program at a time. Although you have all that stuff opened up, there's no need. In a Unix box, you got a Unix terminal, you might have multiple users simultaneously connected, running programs simultaneously. Which means if I had a split personality, or if I had 3 people standing next to me, and I went to a Windows box, and I opened up PowerPoint and said, hey, I'm going to give you guys a presentation, I'm going to show you PowerPoint. I can't check my email right now. In a Unix system, you can check your email. You can have another user standing, hey, move over, okay, make room for the new person. And they're playing with email while I'm playing with PowerPoint. And this actually happens. You can actually log. If I opened up a port on this computer, you could log into my computer through my Apache server. And you could check my email while I give this presentation simultaneously, which is what you get in a Unix environment because you have multi-programming, multi-process, multi-thread mapping to each process. So the environment is set up to be a distributed computing environment. So you always see companies. You know, nowadays, if you have companies and you're buying PCs, you're buying one PC for each desk. Everybody's got their own computer. If you're going the Unix route, you buy, how many users do I have? 200 users. Okay, well, you can give me 2 boxes. You put 2 boxes out there, 2 computers, and you got 200 terminals with keyboards. And maybe you have like a local, you know, hard drive or something, who knows. They could be fat terminals, fat clients, they could be thin clients. You connect them to these two boxes. Everybody's sharing the same process. Everybody's running the same programs. Everybody's got their own files. You have the abstraction of having your own computer. You're opening email and Power. Obviously, you're running multiple things simultaneously, which is the hugest, biggest difference between distributed, multi-processing, multi-programming environments versus single desktop, single user computers. So anyway, long story short, in the old days they used to call these, they don't call them anymore, now they call them personal computers. There's a reason why it's called a PC. It's personal, it's not shared. Only one person at a time can run one program at a time on this computer. Multiple people can't use it, it's personal. So that's why it's called a PC. Versus a Unix box, which is not a PC. It's multi-processing, multi-programming. All right, enough was said with that. So after execution of program number 2 in the child, program number 2 is a CP in this example, copy command. We have after the execution, we have the parent process data, we have the child process data. We have program number 2, text data, we have program number 1, anyway, program number 2, program text data here unchanged. We have multiple different threads running in this one process that's executing different things, that's being managed by the process, long story short. Here's our Unix process generation. Actually, one thing that's mentioned here, which is terminology we get in Unix that we don't get in Windows. If we have the ability to have multiple running processes with multiple threads, we can start a process, fork a child process, kill the parent process, and then go on to something else. And what do we've created? Created a daemon. And so we have daemons that do work. So we can have multiple running processes that just run. Well, I mean, above and beyond the foreground and the background concept. In Unix, we can put a process in the foreground. We can put it in the background. We can switch it back and forth. As an example, I'm running PowerPoint right now. And because I'm on a Linux system, I can actually do this. If I wanted to, I could fork a child process off and check my email. And I could actually, put maybe email up over here, in a little box up here. I could check my email while I'm doing my presentation to you or something. And then I would have 2 processes running simultaneously, and perhaps interact, just to say when I have my recording software running right now and my PowerPoint running right now simultaneously. Not to say you can't do this in Windows, you can, not to steer you in the wrong direction. The quality isn't as good because you have a little delay. In fact, you'll notice there's a little echo. It's not in real time. One's running, the other one's running, one's running, the other one's running. At one point, even on a Unix box, they're not both running simultaneously. The processor can only run one command at a time, unless you have a dual processor system and you have multiple commands running. So, long story short, if I had multiple windows here, I could run things, and one of them would be a foreground process, the other one would be a background process, and they would both be running simultaneously at the same time. So Unix, we've got what's called daemon processes. We've got runaway or processes that block I/O, that take and redirect I/O, so that as example, terminal windows are sort of like that. You log in remotely through a terminal window. Nobody's going to see your output. It's just going to show up on your window. So you've got redirecting outputs. You got processes that can't die. You got processes that die. You got all sorts of different things that you can do in terms of flexibility. Unix process genealogy here. This is what I was talking about before. So Unix starts up, the kernel process initiates, init process when forks off the init processes. The init processes start the entire system. Finally, we get to the shell. We have the login that happens, and then we have the shell. The shell is a process. It's a process that runs on top of these other processes. And we have a bunch of stacked up processes. All of these are running in the background. Some of them are daemons, some of them are reachable. If a parent dies before the child dies, the child can't ever die. Because the only way a child can die and get cleaned up by the operating system is if it sends a signal back to the parent. It says, hey, I'm gone now. And then the parent can clean it up. But if you fork a child and you kill the parent, that child's never going to die. It's going to stay out for the life of the until you reboot the computer, essentially. And lot of these guys are like that. They fork off all these processes, and then the parents go away. I clean up the memory. What do we need you for? You know. And then you load on the int log and executable, and all of a sudden you got a bunch of stuff running in the background, and you got a bunch of stuff running in the foreground, and you got a lot of processes running simultaneously. So this is generic. This is each Unix breed. I just call them breeds. Each Unix build is going to have different, similar but different. And the way scripts work in here is each one of these, like for example, there's going to be a login script that's going to tell you to load C shell or Bourne shell or bash or something. There's going to be a login script up here to say create multiple telnet logins, or don't allow anyone to remotely connect. Or another one's going to say start a print server. Another one's going to say start file support and start this and start that. And all these scripts are actually configurable. And another point to make on scripts. These are built-in processes, precompiled programs that are running, and the scripts glue them together, create the organization. So you have a startup script that the kernel follows. It's kind of like instructions. Do this first, do that next, do this next, do this. So you give instruction sets to everybody, and then you can customize the system with instructions, and you can actually set the order in which everything gets loaded. So if you don't want, and this is you know, another example of, let's say, how does Apple make the notebook start up faster? You know, how do we change the user experience? Change the order of the scripts. Change the order of the processes that are being created. Modify, tweak it a little bit so we don't have such a delay. You know, and maybe we'll delay it over here when the user's not going to notice it or something. Or maybe we won't load everything right now. Maybe we'll only load part of the stuff. And you know, Windows plays with that too, because everything's about the user experience. So you want the computer to load up fast. If you haven't noticed, in Windows, once things load, things really aren't loaded yet. Although you have the impression that the entire computer, and this is the same on a MacBook as well, you have the impression that the entire system is booted up and loaded and ready for you. You know, there's still stuff going on in the background. It's not really booted up yet because you still got processes that are forking off from the kernel. And this tree has to be built. When the tree gets built and when it's finished is up to the operating system designer. Process permissions. So we have real IDs and we have one or more real ID groups, so real group IDs that are set at login. We have effective user IDs and effective user ID groups, group IDs that determine process access to read, write, execute, search files and directories. UMask, which will deliver the file mode creation mask used when the file or directory is created by a process. Sets a UMask, says, hey, you're owned by you, and you can do this and you can do that. That is how the kernel can create user directories, and how you can actually, you know, set a mask on a directory to say only bhackers allowed to bhacker off of home. And Jane Smith only has access to Jane Smith directory, but I didn't start that directory. The kernel started it for me. And then the kernel ran my login script for me, and the kernel set my mode correctly. And this is what the system administrator is doing, is configuring all of the kernel stuff. So system calls work from user mode to kernel mode, and it tells the kernel to do something. Signals go from the kernel to the user and tells the user that the kernel is doing something. So we have communication in both directions, user mode to kernel mode to user mode. So a signal is a message a process can send to a process or a process group if it has appropriate permissions, which means you can't communicate. So if I installed that Bluetooth application on your phones and you were chatting amongst yourselves over here, if you weren't part of the group, you weren't in the clique correctly, and I'm sure you guys have cliques too. Every group of students has cliques. Then you can't talk to us. You can't chat with me. You know, I'm in the wrong clique or whatever. Okay, no problem. That's what happens with the processes. Kernel mode processes are like off limits. You can't talk to those people. User mode processes, kernel can talk to the user mode processes all they want, but user mode processes can't talk to kernel mode processes, nor can they communicate or do anything. If you created a process, your process can't talk with anybody else's process, but your processes can talk amongst themselves. So we have signals that send information back and forth between processes. Normally the traditional use of the signals is for the kernel to tell the user mode something, because the kernel can talk to the user mode processes all they want. They have that permission. But the user mode never talks to the kernel. It goes through the system call interface to talk to the kernel processes, which is why most traditional extractors will say, a hardware device sends a signal to the kernel, and our kernel sends a signal to the user mode. But theoretically, if the permissions were granted, the user could have sent a signal down to the hardware, actually. You can generate user mode signals. That's part of the language. It's part of the interface. It's not off limits. The only problem is all those kernel processes are completely off limits. So you can't send a signal to a kernel process. So for each signal, because we can send signals between signals in the user mode, and we can also, if we're given permission, message numbers. Okay, so the signal itself, by definition, the message of a process that can send to another process or process group as appropriate permissions. The message number represents the symbolic name of the signal. For each signal, the receiving process can explicitly ignore the signal. Doesn't mean they have to pay attention to the signal. Specify an action to be taken upon receipt of the signal using a signal handler, or otherwise default the action that takes place. Usually process is killed on a default action that receives a signal. If, for example, you're in your user mode and you press Control-C, you are generating a signal. It's from a hardware interrupt that is being generated from the pressing of the keys that's going up to the kernel. It says, the user pressed Control-C. We have Control-Z to pause, Control-C to quit. We have, actually there's a ton of those things out, not too many, a handful, that generate signals. We can do signals, we can generate them from a software perspective as well. We can generate them from the hardware. So we have choices in which we're generating. We can capture them, we cannot capture them. By default, the kernel has a signal handler that is used as it's a vector table that keeps track of all the different signals that are available. Which ones has it received? Because if you think of the concept, if you press Control-C like 10 times, does it have enough time to respond to it between all the different presses? The system's not going to respond that quickly. It's going to lose half of those signals that you sent, which is why actually you have to do it like a couple of times. You just can't press Control-C once and the whole program is going to stop for you. You usually have to bang on it a couple of times, like 20 times, because the signal has to be captured, and half of them are going to be lost in the process. So, from an operating system perspective, when a child exits its signal, a child signal is sent to its parent, so the parent knows that the child exited. So that's a process that sent a signal from a process that was generated by a process from a software perspective. When the parent issues a wait to tell the system that it wants to catch the child signal, the parent sits there and waits. That's a signal that the parent sends. When the parent does not issue a wait, it ignores the child signal. It means it just created a child that's never going to end. We have a parent that can't end because that's a parent that's a child of another parent. Which brings us to the concept of interprocess communication, which is core to Unix and Unix development in terms of systems programming, systems applications. We have related processes that can communicate with each other. We have signals that read-write to regular files, and we also have pipes. Pipes are direct line of communication using interprocess communication. So we have, in the Unix environment, we have two forms of interprocess communication. We have message passing and direct communication. Message passing is usually in the form of a mutex, or it's usually in the form of a shared variable that's created, where one process looks and says, or checks a mailbox. There's message passing that's actually implemented in terms of kernel level support that uses a mailbox technique. That says, let's check the mailbox. Does we got a message in there? Oh yeah, process number 1 said it wants to start running. Can we stop for a second? And one process stops and the other process starts running. Or we have direct communication that runs between processes. That's usually sent by signals and by other different mutexes and other different techniques to make one process stop. or make another process start, or control the interprocessing. This is the communication channel that the kernel uses to control its processes. You can also write programs from a user mode that taps into all that kernel support using the system call interface. So this is where most of the systems programs come into place, and they go, well, you know, let's do a pipe. Well, then what's a pipe? It's a form of interprocess communication when process B tries to read from a pipe and process A tries to write to a pipe. In fact, the pipe symbol actually looks like two lines usually when you program it or when you use it from a command line prompt. You can actually use pipes. In a command line prompt. You can actually program with pipes. You can create pipes as well. And people are usually at this point, well, it's just like plumbing. If you turned on your sink, how's the water going to get there? Well, you take the water source, you connect a pipe, you connect it to the sink, you know, or the drain pipe. You know, has a drain pipe ever broken on any of your sinks? Usually happens in the kitchen sink. And then you open up the cabinet below the sink. Oh my God, it's flooded in here because the pipe was broken. Pipe is just nothing more than a plumbing pipe. It's the same context and the same usage. You open up a pipe, you send water through it. It goes from point A to point B. In this case, from a Unix perspective, the pipe is an interprocess communication mechanism. It's a channel, it's a line, it's a direct form of communication. And it actually gets implemented in the form of a process. The process goes and listens to one end and receives on the other end. And the process itself and the pipe, in terms of its abstraction and its implementation, does nothing more than connect two programs, program A and program B. So what is program A doing? It might be reading and writing to a file. It might be opening up something. It might be providing terminal access or something. When you pipe in information, you might be redirecting it from one source to another. So in terms of the concept, you usually have a process connected to both ends of the pipe, and you send stuff back and forth between the processes using the pipe, which is why half of those assignments that you're doing, some of them you'll actually have to use a pipe, because you'll have to connect, you know, send the output of this program to input of that program, and run this other program, and use it with that other program over there. And how are you going to get them all to communicate? Well, you got to create some pipes, or redirect the output and the input, which is another form of doing a pipe, actually. Because if you're outputting and inputting and redirecting I/O, works great for I/O. But what about program execution that's not I/O? And then you can just use a pipe instead of redirecting I/O. So there's different ways of doing it for different reasons. So in this example, when process B tries to read from a pipe, it returns data if process A has written to the pipe, returns with end of file if there's no other process, has a pipe open for writing, suspends the action until process A writes the data to the pipe. So you have two processes listening to some communication channel, waiting for some event to occur, and they respond to the events. So a child returns that the exit value to waiting the parent process. So in terms of interprocess communication, we have some, and those, believe it or not, were things for processes that were related to each other. They're all owned by the same process group, or all working together, or all user level, or all kernel level, or all part of related processes. We have unrelated processes, which fall into the name of named pipes, which is the category of direction. So we could send I/O from a process that we own to a process that we don't own. You know, in fact, that happens all the time, actually, when you redirect I/O. We can implement it for certain situations in terms of a first in, first out, kind of, you know, stacking up in sort of a buffer. We can send up information for unrelated pipes, store it in a buffer, and deliver it, kind of like how you deliver messages back and forth to the Postal Service. System V IPC messages, not supported on all systems. We have message queues, semaphores, shared memory. Usually between processes that aren't related is when you're going to be implementing that. Or lo and behold, sockets. So this is where Unix and networking come into play in terms of the client-server model. And if you're in the Java EE course, I've been talking about sockets for the last couple of weeks, actually. underlying implementation of RMI, underlying implementation of TCP and UDP over IP, all uses socket abstraction. Socket extraction opens up a form of an unnamed pipe called a socket. You create a socket from one computer, you create a socket on another computer, and you're communicating between processes between two different ports. Sockets are usually bound to ports. Ports are usually hopefully opened, unsecured, so that you can enter in and enter out. It's kind of like if you took a big old pipe and connected it from your water source over to your neighbor's water source. You'd have client-server computing where you've got a socket, I don't know, a hose socket or something from one house going over to another house, and both of them are sharing the same water source. Then what you end up having is a socket abstraction in terms of networking. So I guess that's kind of like how you steal cable from your neighbors, or wireless access to. But from an example, from an implementation, it has nothing to do with it, but from an abstraction it's sort of similar. But anyway, as for sockets come into play, socket's nothing more than ability. In fact, when you do socket programming and you create a TCP or UDP kind of extraction, you're actually creating a pipe. It's another form of an unnamed pipe that's running between the different sockets. So instead of connecting processes, you're connecting ports, and the socket itself provides that abstraction. So process environments include process IDs and process group IDs, open files, current working directories, real and effective user and group IDs, file creation masks, which is the UMask, resource limitations, signal action settings, and a set of named local variables. So that's kind of what the environment includes. In Unix, we also have this concept of the file descriptor. And one last comment to make in terms of interprocess communication by definition. If you take an operating systems course, you end up looking at and having to study all of the different modes of interprocess communication and all the different concepts of deadlock and starvation and all of the different things that happen when you start getting multiple processes to communicate with each other. And that's more of an operating system implementation issue, because all operating systems, regardless of whether they're Windows or Unix or whatever, have to worry about what happens when processes don't cooperate well. So that's an entire breed of process management that goes on, so that you don't have one process blocking another process, or not allowing that process to run, or you don't have two processes trying to open up a CD-ROM drive at the same time. And every single operating system out there has problems with interprocesses and communication between them. Because lo and behold, inevitably, you'll have a situation where the computer will lock up because something is deadlocked, or something is starved, or some process is not communicating well with the rest of the processes. So it doesn't matter what operating system you're talking about, there's no safe operating system that's running with multiple processes. So most real-time systems don't do very much multiprocessing. Not safe. They do one command after another command after another command after another. It's mostly sequential processing. Multiprocessing, that's for home users. That's for you guys. Because it was created as a concept for user interface, for experience, for giving you the user. A lot of modern day issues are designed to provide you with multiple things running simultaneously so that you don't get bored on your computer, I guess. Other more reliable systems, I'm trying to minimize the amount of multiprocessing. The more you can minimize the amount of multiprocessing, the safer, the more reliable the operating system actually is, because you don't have to deal with those issues. All right, so that was my concluding thoughts on the concept of multiprocessing. Another important feature to consider in terms of files and processing on a Unix platform is this concept of the file descriptor. We have file descriptors that we can actually create. So each process associates a number or a handle called a file descriptor, and FD for short, for each file that is opened. Because here's the thing, you don't want to actually read and write to the secondary storage or to the file. And in Unix, file is everything. We have a file descriptor for a USB drive, which is a device descriptor, aka file descriptor. It's a pointer to the memory that's storing the information that's communicating with the hardware device. Directories, files, devices, everything is a file. Everything uses a file descriptor. So we can keep track of everything that's part of the picture in terms of numbers. We have file descriptor tables that says, oh yeah, that's over here. Oh yeah, that's over here. So it knows where to find all of these different resources on the computer simultaneously. That's how Unix does it through file descriptor. Actually, Windows does it in a very similar fashion as well. It's kind of a common way of keeping track of resources. So at login, 3 files are associated with the terminal. This is where we're getting standard input, standard output, and standard error. And that's where we get 0, 1, and 2, which are the file descriptor numbers that are associated with standard input, standard output, and standard error. So a lot of people get tricky and they say, you know, take it from 0 and send it to my file. So that's like redirecting the file descriptor 0 to a file. So all the input you're typing is going into a file instead of being executed, or instead of going where it's supposed to be going, or something, blocking the input or something. Redirecting it, actually, in that case. Or opening for writing or reading and writing. So standard error is an open for reading and writing. Standard output is for writing. Standard input is for reading. Read into the input. So this is where those 0, 1, 2 file descriptors come from. In lower level libraries that aren't using like high level APIs, low level system calls, you use the 0, 1, 2 to get to standard in, standard out, standard error. In fact, in Perl you can use 0, 1, 2 instead of putting the capital standard in, standard out. So it's the same equivalence. You're using the file descriptor instead of the name of the particular process. And they're all loaded in the form of a process, actually. So process inherits parent file descriptors unless specified. Close on execute, actually, would be a specification. It says, shut this process down after it's done executing. So actually, it's kind of like the close on exit. That's how I originally read it, because I'm so familiar with the DOS prompt window and the close on exit that happens automatically. So if you've ever run a program that didn't ask for anything, it's just putting, if you run Hello World in Windows, the screen flashes in front of you and goes away. That's close on exit. It's actually kind of the same meaning in close on execute, which means run the program. When the program's done, clean up the mess. Remove the process from the process control block and get rid of the memory. Clean it up, which is what you're doing in Linux. It's the same equivalence, actually. Process subsystem utilities, and this is where all of this set of controls come into place to deal with the process. As I mentioned PS before. Monitors the state of the process. You type in PS. There's another one called jobs, which is not part of this list, and it's not supported on all operating systems. All Linux operating systems, only a subsection will actually support the word jobs. Kill, wait, sleep, nice. Make it nice. Run a process at low priority. That means you're nice. Actually, you can do that in Linux and Unix. Let's say, for example, I'm running this program here, and actually my recording software is running nice. I had to do that, actually. In fact, there was a setting I had to set to do that. Otherwise, my PowerPoint, every time I pressed the up and the down, it took too long. So when it's nice, it means when something is happening on my PowerPoint, let it happen first, record second, which means go at a little lower priority in terms of what you're taking up, in terms of resources, processor time, and stuff. Can you use nice in a Windows system? That'd be a nice feature to add to Windows 8 or something. Because some programs like my web browser, I'd like that to work a lot faster. Load that a little faster than my email program. I'm not really concerned about how often my email program is up to date. It can run in slower priority, which means it gets less CPU time, which means it doesn't run as efficiently. It runs a little slower. But my web browser, I want that to run faster. So, I don't know. You can do that with download. Actually, you can do that with some network utilities. We'll do nice on make some things, minimize processor activity. Some features some features on your computer will eat up processor time if you haven't them turned on. So anyway, set user ID, set group ID mechanisms patented. Basically, you want to process the effective user IDs that are different from real user IDs. When it executes a set user ID and set group IDs, which is essentially changing ID notifications, ID things. So the process effective in user ID groups becomes more of an executable. Things, for example, changing your password would be a mechanism for that. Security problems. Do we have security problems in operating systems? All the time. Unix is no exception. Permissions on executable files and programs. Usually people go to the extreme on Unix for some reason. And set it so most user complaints that go into a system admins, I can't access this. I can't access that. I'm having a problem running this. I'm not mapped to that. And system admins actually spend most of the time just mapping users correctly. Oh, I didn't know you needed that utility. Here, I'll give it to you. The problem is you don't want to give them too much, so you end up giving them just enough. And then you notice that the person over in HR, why are you running Perl? I didn't know you knew anything about Perl. You're not one of the system developers. We didn't map you to the Perl drive, to the Perl application. And then you end up giving them, oh, well, let me just give you full access to the development tools. And then you end up getting everything because everything's in groups. So permissions to directories in which the contains must be correct, otherwise easily replaced by Trojan horses as well. If you have access to something, anything that enters your computer also has access to it, which is why the CGI port is kind of unreliable. It causes security issues. You're going to open up a directory on your Unix server and give it public access. Well, you're not sticking anything in public HTML outside of HTML files. No problem, but when you start opening up other directories, which is how CGI works, you're just giving permission to a directory, which creates a gateway. Then you're allowing anything in that directory. Well, those are executable files, so just replace an executable file with another executable file that's a Trojan horse. And then the next time the user comes in and runs that file that's been replaced, because you gave it public read-write access and everything, then it's going to spark off a process that's going to delete everything on the server hard drive or something. It's going to do something that was totally unexpected in terms of the behavior or something. Or it's going to open up another port. It's going to do something funny. Unpredictable behavior. So it's a nice way of opening up your Linux server, your Unix server, to potential problems. So CGI definitely has some issues associated with security. Some systems remove set user IDs and set group ID bits whenever files are modified as a security precaution. So I can't actually get at that, because if you can find out who owns what, then all you have to do is log in as that person, or pretend like you're that person, or set your user ID to be equal to that person's user ID or something like that. So. The next section is an overview of shells. We've got choices. We could take a mini break, or I can continue. I can talk all day. But I don't know if you guys can sit all day. We want to continue going, or do we want a mini break? Someone's going to answer. Mini break? No? Keep going. Keep going. All right, we're going to keep going. If you have to go to the bathroom, get some water, I don't know, answer your cell phone, please take a mini break. Oh, that's a good question. Let me take a look at my timepiece. That's the problem. I didn't pull it out at the beginning. What time do I plan to end a lecture versus what time will I end a lecture? It's 2:45. I want to get through this today. How about I end it after this? I want to get through shells today. Or you got choices. If I actually go till about 3:30 today, then tomorrow we'll get out earlier. If I end it now or within the next 15 minutes, well, I have to finish. I have to cover the material whether I cover it today or tomorrow. I would prefer just keep going. Let's just keep going. I'm going to keep going. All right. And we'll get out maybe about another half hour. Is that all right with you? Do you have a plane or something to catch or no? Are you good? Okay. You're just trying to plan your day is what you're trying to do. Yeah. You're good? Okay, good. Just sleepy? There's a coffee machine. I just had some coffee. And that's my problem. I had coffee. Oh, really? Not for students? I got to put something in for that. That's bad. We need to serve coffee to the students. Otherwise, I would have these everyone in your room going, yeah. Continue. You'd be as wired as I am right now. Because that's pretty strong coffee they have for the faculty. All right, let's continue. This isn't actually that bad. I might even get out a little bit before 3:15. In fact, I'm suspecting, if I actually start this lecture soon, expecting about 15-20 minutes. Well, let's see what happens. All right. I don't know how many slides there are in this. 40 what? 45? Oh, that's 15-20 minutes. We're good. All right, I'm going to start. All right, thank you. Welcome back from the break. Now we have an overview of shells. We actually have covered most of the stuff already because I talked about shells, and I talked about scripts a little bit when I talked about Perl earlier today. What is a shell? It's a command line interpreter and programming language between the operating system and the user. It's our user mode. It's our abstraction of a user mode. When it loads up, it loads us a shell. We get a shell. That's why a lot of people don't like Unix. A lot of people are afraid of Linux and Unix because they sit there at this like flashing cursor at a shell prompt and they don't know what to do because they grew up on Windows and all they're familiar with are icons and a mouse. There's no use for a mouse in a shell normally. The keyboard is useful. And so in the old days, before we had, this is like in the old days when we used to walk 2,000 feet, no, excuse me, 2 miles in the snow uphill, barefoot, carrying backpacks of books to go to school. Because everybody's parents always gave you that story when you complained about having to take the bus or something. You know? And when I was your kid, anyway, before we had Windows, we had shells, and when we loaded up the shell, we had to memorize a bunch of commands. And in fact, people used to have books, notebooks, full of these commands. You memorize the commands, you type in the commands, and then people got smart, and they started adding features to shells. You know, like history. So if you'd already used the command once, you could reuse the command. And then shell variables. And then, well, why don't we just make it so we can put stuff in the environment variables so we don't have to keep typing it every time. And then some people got smart. Well, what about scripts? And then the concept of the programs came around. And well, what about executable files that we could just write in C and then run them from the shell? And then voila, we have Windows, which is essentially the generation of how shells turned into GUI. Well, not in so many words. I mean, that's a simplified version of it. But long story short, we had tons of different shells that were created for tons of different purposes, and everyone decided in the end, by the time of Windows and by the time the desktop concept came around, all the shells end up becoming equal. But in the old days, the shell was the equivalent to the desktop. And you're still going to find this in Unix and Linux communities. We have the desktop. What is the desktop? It's KDE, it's Ubuntu, I think it's called Unify or Unity. I always say that wrong. I always get corrected. But let's just call it GNOME. There's GNOME, Genome, G-N-O-M-E, if I'm saying that right. I know I can say KDE correctly, but anyway, Ubuntu's got a new one out as well. I think it's called Unity or Unify or something. But long story short, these are just different programs. They're executable programs that are shells. What does a shell have? A bunch of icons, and a file menu, and graphical user interface instead of a command line interface. So a shell and a desktop are the same thing. The desktop allows you to double click on icons or single click or whatever, and use a task menu and file menu and all, task bars and all those GUI components. Equivalent. Anything you do in the GUI you can do from a command line interpreter. And the command line interpreter is just the same thing. So people modern day, they have a shell and they load a GUI. They load KDE, they load Genome or something on there. If you're a Windows user, you have that automatically. If you're a Mac user, you have that automatically as well. You have BSD Unix with OS X, or the OS that's loaded on top. It's a shell. It's a graphical user interface to the underlying Unix system that's underneath on the computer. Windows, not quite the same abstraction, but it's the same thing. Okay, so the problem with a Windows system, which is actually kind of different than a MacBook, you can go to a terminal prompt, you can actually change it. You can actually load on KDE from your, KDE is a desktop actually, just like Windows or whatever. It's a windowing system, but you can actually, to a minimal extent, you can't get rid of OS X, but you can add things to create different desktop environments if you're working with a Linux kernel. you can't buy an XP box or install Windows 7 and change the desktop to something else. You're stuck with Windows 7 or XP. You can change the look and feel, you can modify it, but the shell as a concept is fixed for you. And for the most part, OS X runs the same way. It's pretty fixed. You got to go out of your way to get something else to load on that. Unix, Linux, however, is the opposite way around. You get nothing. You don't get any graphical user interface at all. In modern builds you do, it installs automatically. But in the old days you got a prompt, a command line prompt, and you loaded a shell on top of that, and the shell was the graphical user interface. And it was a program like KDE or GROM or any of those other ones I've been mentioning. If you didn't use a graphical user interface, you used a command line interface. The command line interface came in a lot of these different forms, and here are some examples users may select from. C shell, corn shell, bash. Actually, BSD uses bash as a core shell. Then we had shell scripts. So files in Unix and shell commands are executed from a Unix shell. So they were just text files that contained scripts. And the scripts were written for the shell environment, and the scripts performed stuff that the user wanted to do, and you just ran a script. Now, modern day, you double-click on an icon. It does the same thing, essentially. In terms of working within the shell, this shell invokes automatically during the login session. You select which shell you want, gets loaded. Now people select graphical user interface shells, and that gets loaded automatically for you. At the prompt by the user, actually this is a good test. Actually, you can see the entire abstraction on your Android phones. Actually, you can see it on an iPhone too. iPhone runs the same way. Actually, there's a kernel under there, and it loads the shell on top. And so if you set the mode correctly, you can see all the command line stuff of everything that gets loaded, then all of a sudden the GUI comes up at the end. Most people have that hidden, so you can't see that. But the same concept is happening. The Linux kernel is starting, systems loading up, and because Android is Linux, it's run off a Linux kernel. Same concept as a Linux box or Unix box. So the kernel loads up, the shell scripts load up. You can change the shell scripts as well. File system initializes, and then the GUI comes up. And you make modifications, change the GUI. Actually, the GUI has changed a lot between all the different versions, and it's gotten a little better actually. But I kind of actually sort of somehow prefer some of the older ones though. Anyway, long story short, it's a shell. So it reads the shell itself in terms of working with the shell. The shell reads a specific startup file for initialization, sets parameters, sets environment variables, displays the prompt, and waits for the user commands. Execute user's commands, and then it goes to step 2 until Control-D, and then happens, perhaps, unless Control-D happens, which is going to be a pause or a stop, and then the shell terminates. The shell always ends. So redirection of input and output in a shell. This is where you can say man ls go to redirection, go to info.ls, and I actually covered this in the first weekend. So we looked at these commands already. Redirection of output, redirection of input, the arrow just switch it around. So if you think about it, C in and C out, that's why we've got those little arrows there. It's actually a redirection operator. So if you've learned C++ and you've used C in and C out, you're redirecting output with that. It's an object that redirects output to another object, and the output standard I/O or standard input, depending upon where you're reading or writing from, whether you're using C in or C out. So it's very Unix-like actually. Using files and pipes, and here's that pipe command. As I mentioned it before, it's kind of a line that goes up and down. So cat is going to take one file and pipe it to take this file and send it to word count. And word count is going to count how many things are in that. -1, I don't know what that means. Maybe it counts words instead of lines. Oh, it counts lines actually, unless that's an L. It counts the number of lines in a file. So we have some shell core features that exist, simple and complex commands, redirection of input and output, which is kind of a core concept for shells, pipes, wildcards, command substitution, background processes, foreground processes, obviously, shell variables, here documents. I'll save here documents till tomorrow. I'm going to give you the abridged version of this lecture. Built-in commands that exist, and also programming constructs. The C shell actually allows you to type and write in C programs and compile them right there in the shell without actually having to use a compiler, because the shell acts as a command interpreter for your C command lines. Simple commands supported. So the simple command is a sequence of non-blanks arguments separated by blanks or tabs. So the first argument is the numbered 0. It usually specifies the name of the command to be executed. And any of the remaining arguments, with a few exceptions, see the meta characters. Well, actually, look at that up online in the man pages for shells, and you'll kind of see what kind of meta characters exist. For passing arguments at that command, for arguments that may be files, file names, we see this. In fact, we looked at this earlier before lunch when I talked about command line arguments. The command line arguments is everything that gets taken. Command argument 0 is the name of the file that you typed in. All this information that's coming in from, that gets past the main and gets parsed, as we talked about earlier, and gets usually put in the form of an array that's supported in Perl, but it's also standard C, actually. And it works in the shell environment as well. And what that does is it allows you to run programs with parameters, and inside of the program you keep track of the parameters and stuff like that. It allows you for basic functionality, and that's actually where we get this concept from that's implemented in programming languages. In fact, this is the root, because everything that we're running on a computer, we're running in the form of a shell, and the Unix kernel, or the kernel, depending upon what breed of operating system you're on, is the command interpreter, and it's actually reading what it is you're sending to it and processing it. Most shells also support complex commands, multiple commands, command groupings, conditional command execution, file name expansion, wildcards. So when we use give me star.star, it's the shell that's interpreting the wildcard and finding the information for us. Or list out, list matches any of the any character in the list. Lower upper to upper, upper lower. Changing the case of characters is a shell kind of thing. Most Unix people are familiar with the concept of shell scripts because that's how they get stuff done. It's like writing programs without actually having to compile programs. And I've kind of gone over the concept of scripts and why we write them when I talked about Perl. So the shell script is a regular text file, contains the shell Unix commands. So before running it, you must have to have executable privileges to it. We talked about this morning with Perl, so I don't have to repeat that. Very useful for automating repetitive tasks. So before the concept of scripts came into place, people would have to memorize a bunch of commands and keep typing them in over and over again. And if you do that a lot, it can get kind of redundant. So I've actually written scripts on my computer here that I run. I open up Command Terminal and I run a script. What does that do? Well, for me personally, it takes my Android emulator and connects it to Eclipse and sets up the environment and starts this and starts that. So I can just run my script, go and get some coffee and come back, and all of a sudden everything's ready and configured for me. Ready to go. And what I've done is I glued together a bunch of pieces from a bunch of different programs so they can all work it together in some automated development environment to make my life easier, kind of thing. In fact, there are some people that use what's called the startup. You're all familiar with that in Windows. And then you load anything you want in the startup menu. That's another form of a shell script, if you think about it, because when you turn your computer on and you log in, it loads your email program, loads your Firefox, loads everything out. Whatever you put in the startup, it's a script, if you think about it. It's loaded as a graphical script, but it is a script. So when the script is run, the kernel determines which shell is supposed to be used. And you can specify the shell in the first line, as we've seen with Perl. That syntax you might look a little familiar from this morning. We're just going to put the path name and the script name in there. So the first line with this hash, this number sign, when it's interpreted by a C shell with a path and then an executable file, it's going to basically tell run this shell. So, and for a long time, people started writing their own shells. You can write your own shell, actually. If you take my operating systems course, you do write your own shell. So you can write your own shell and have your own commands. And what does that do? It gives you automated, I do have here documents in here. It gives you an automated environment for which you can, customize your user experience. So we have this concept of here documents. One of your assignments actually has you create a here document. In fact, the shell script environment has you do that. So at the end, I'll have to make sure to tell you which lecture number this is again, because I can't remember. And I believe it's either the last project or one of the assignments. says write a here document, and I usually get about 15 million messages from students. What's a here document? So slide number 37 here is the here is the here document. Huh?
This one.
Just one page, one slide. Yeah. One assignment. There's only one assignment too.
Huh?
There's only one assignment that works with one slide. Yeah. Project number 3 works with the here document. Is that the one where it takes you send out a message using a script? You create a document that inserts people's names and sends emails out. Don't send those emails out, by the way. Pretend. Don't send emails out to here documents. Well, here is a shell provides alternative ways of supplying standard input to commands. So the shell allows inline input redirection using these redirectional operators called here documents. So you're writing a here document that takes, "Hi Susie, thank you for showing up and meeting your attendance requirements," and you're sending it out to all of the students in the class, or all those people who are on the attendance list, by providing this script with a list of email addresses, the text that you'd like to send them, and then you create this here thing that sends all these commands with arguments and the command input and arbitrarily just runs them. So the arbitrary delimiter should be a string that does not appear in the text, and the arbitrary delimiter is given with the here, which is the redirectional. Basically, it allows inline input to say, here are all the names, here's the message, and here's my email program, and do it, is what you're doing. And the script is basically just, going to take this message and send it out to everybody you want to send it to. And actually, you can insert in the message, I believe it has you insert the person's name or something. And you can play around with that and figure out what to do. But that's what's meant by a here document. It creates on-the-fly inline input to go into a script. Not a document called here. Here.doc. It's a joke. Okay. All right, you guys aren't too happy right now. You guys are just tired. So, shell variables. There are several different mechanisms for creating variables. A variable is a name. It's a name memory. It's a named identifier representing a string value. Shell variables can save time and reduce typing errors. And it can save the path as a variable. It is a path. It's called path. It's an environment variable. PWD. Password is also one used for a different purpose. So we have two types. We have local and environmental. Locals are set by the user, by the shell itself. And then we have their positional parameters, variables that are normally set only on a command line. And environmental are the ones we have print environment. We see all the environment variables. So if we're setting it per user, we're putting it in the login script, and we're setting environment variables. No matter which shell you're in, you have access to those variables. You could also create a bunch of variables and use it for particular shells. And every time you load the shell, you have those local variables. Why do you want to do that? So you can automate stuff. You can set the prompt to look a different way, or set the name of the user to be something else. It allows you to kind of customize the system. This stuff we've seen, I can just kind of jump through it. Home, path, mail. Nobody uses mail anymore, actually, because everybody's got GUI mail systems. There's text-based mail still exists. Positional parameters, where we have same concept as the command line arguments and the parameters that are coming in when you run a program. The shell picks it up, and you have positional 0, 1, 2, 3. Name of the program, the first argument, the second argument, the third argument. So when a shell procedure is invoked, the shell implicitly creates the positional parameters. The name of the positional parameters is a number. So number 0, 1, 2, 3. It actually, in C APIs, it creates an array out of it as well. So I have to go through that. Quoting. Quoting restores the literal meaning of the characters that are processed specifically by the shell. Instead of actually running a command, we use quotes to say, well, we want it to say string. We don't use string. So the literal quotes are not passed on the command line. Single quotes. The single one inhibits wildcard replacement, variable substitution, command substitution. The double quotes inhibit wildcard replacement only. quotes are nested. Only the outer quotes have any effect. The inner quotes don't actually work, which is kind of interesting. Every shell has built-in commands. Every Windows program, every Windows shell has built-in commands. Commands that are internal to the shell, faster to execute and more efficient than other commands because they load up when the shell loads up. They're part of the shell process, which is why Windows commands will always run faster than any command you run on top of Windows. Shell does not have to fork off a process to execute the command. It's part of the current process that's running. Trade-off. Redirection of input and output are not allowed for most of those commands. Well, how can you? You don't have a process to deal with. As we noticed, input and output between process communication, that's how it's facilitated by piping or by creating some sort of a direct message exchange. Can't do that if you're talking to the master process that created you, that gave you that command to run. Built-in commands are common to 3 shells: execute, echo, change directory, evaluate. So built-in commands are sort of like what most people are familiar with in terms of DOS. Exit to a DOS window, you get dir, rename. All those commands are built-in commands. And these shells have the same thing. So that was quick. See, it's only 3:10. So, what I'm going to talk about tomorrow, we're going to end today actually. So unless we have questions, do we have questions? I'll let you sit at this for a second then. What are we going to talk about tomorrow? We're going to talk about shell scripting. So we're going to look at C shell, compare it to some of the other shell scripts, talk about shell scripting a little bit more, and then we're going to go into some miscellaneous Unix topics that everybody who takes a Unix course should know about. And then we'll conclude all of the information that you're going to need for the rest of this course tomorrow, which is not really that much more actually. Questions, comments, or concerns? Tomorrow we're starting up at 10 o'clock in the morning. In fact, this is really the end of part 1 of this lecture. So somebody has to remind me. I forgot about this part. I'm not going to cover it anyway, but actually it wasn't part. I pulled it out, but I left that one slide. So forget what I just said. I already corrected myself because I know it's in a different lecture already. So that slide was actually getting into the concept of subshells and different types of shells. So let's cover that tomorrow. It's a total theme for a different lecture. So let me end this video.